This DIY $50 machine can supply a house with continuous power for up to 50 years. It does not rely on the sun to shine or the wind to blow, and continuously operates at a capacity of over 95%, a level of reliability that neither solar nor wind can match. Yet despite the technology having been known for nearly 250 years, we're told the key to energy independence is to spend thousands on PV solar cells or lithium-ion batteries that degrade in a matter of years. This is called a Pico Hydro generator, and by the end of this video, you'll learn exactly what they are, how they work, and how you can start making your own right now. Let's dive in. Utilizing the flow of water as a power source has been a trick that civilizations have been applying for centuries. Over 2,000 years ago, Greek engineers developed the first water-powered machines, simple horizontal wheels set directly in a stream's current, transferring its energy upward through a vertical shaft into a millstone. They were rudimentary by any modern standard, but they established a principle that every hydroelectric station on Earth still relies on today: the conversion of kinetic energy in moving water into useful mechanical work. By the 2nd century, Roman hydraulic engineering had taken this principle one step further. At the Barbegal complex, in what is now southern France, 16 overshot water wheels were arranged in 2 parallel rows, each positioned to exploit the vertical drop of the water, what engineers call head, to multiply the force of the flow. They understood that power was a function not just of how much water was available, but of how far you let it fall. They mastered this principle so brilliantly that this single site could process enough grain to feed 12,000 people. But if we fast forward a few hundred years, then you'll arrive at a time when the modern era of independent hydropower was starting to take shape. It began with an accident in a Sierra Nevada gold mine, and a carpenter named Lester Allen Pelton, who happened to be watching when it occurred. In the 1870s, mining operations across the Sierra Nevada were consuming entire forests to fuel their steam engines. The water wheels available at the time, crude, hurdy-gurdy wheels with flat blades, were lucky to reach 40% efficiency. Pelton was observing one of these wheels when the pin holding it to its drive shaft slipped, and the jet of water aimed at the center of the buckets struck the very edge instead. But instead of slowing the wheel down, against every expectation, it sped up. What Pelton recognized in that moment was one of the most productive observations in the history of mechanical engineering. It was not enough to strike a blade with water. The key was to reverse the water's direction as completely as possible, to extract every ounce of momentum. He designed a bucket with a central ridge called a splitter, which divided the incoming jet and turned it 180 degrees. By 1880, his wheel had reached over 90% efficiency, allowing remote homesteads and small mines to generate substantial power from high mountain streams, previously considered untappable. In 1878, the industrialist Sir William Armstrong had already used a single turbine to illuminate his home in Northumberland, England, the first private residence in history to be powered by falling water. The term Pico Hydro was soon coined, a term used to refer to hydroelectric power generation under 5 kilowatts. And for a brief window between 1880 and 1930, decentralized hydropower was part of the fabric of Western life. Thousands of remote homesteads and small towns operated individual lighting plants. By the turn of the century, the quiet hum of the Pelton wheel was the sound of independence. But that independence was about to be dismantled. Now, before we dive into how to make your own Pico Hydro plant, it's important to understand exactly how these systems work. Pico systems can come in all shapes and sizes, but unlike large-scale hydroelectric generation, a Pico Hydro system tends not to require damming the river. It uses what engineers call a run-of-river approach, which involves diverting a small portion of a stream without impounding it. The process begins with an intake. The most advanced installations use a Coanda effect screen, a specialized wedge wire grate designed to exploit the surface tension of water itself. Water clings to the curved surface of the screen and drops through into the intake channel, while leaves, sticks, and silt wash harmlessly over the top. From the intake, the water enters a 4-bay tank, where the water slows down, allowing heavy sand and silt to sink to the bottom before the water enters the pipe. The water then enters what is known as the penstock, a pressurized pipeline that carries the water down the slope. This is where the physics of head, the vertical drop, and flow, the volume of water, take over. As the water travels down the pipe, the weight of the water above creates pressure at the bottom. For every 10 feet of drop, you gain roughly 4.3 pounds per square inch of pressure. At the bottom of the slope, inside a small powerhouse, the pipe narrows into a nozzle. That nozzle converts the accumulated pressure into a high-velocity jet aimed at the curved buckets of a Pelton or Turgo runner. That shaft drives a permanent magnet alternator, a generator whose internal magnets produce power the moment the shaft turns, without needing an external electrical source to wake it. It produces raw alternating current as it spins. But here is the thing that makes Pico Hydro different from any other off-grid system. The turbine must always have a load. In a conventional engine, a throttle reduces power output when demand falls. You cannot throttle a mountain stream, as reducing flow through the penstock creates a pressure wave, called a water hammer, that can burst the pipe. So the water always flows at a constant rate, the turbine spins at constant speed, and the system produces constant power regardless of what the house demands at any given moment. To manage this, the system uses an electronic load controller. The ELC monitors the electrical demand of the house continuously. When you switch off a lamp, it senses the surplus in the same instant and redirects it to a dump load, typically a large water heating element or a bank of resistors. In a Pico Hydro home, you don't save energy by turning off lights. You simply move the energy from the light bulb to the hot water tank. When you compare Pico Hydro against the alternatives, it's clear there are some undeniable advantages to employing these systems in an off-grid setup. When it comes to energy independence, we live in a solar-centric energy landscape, in part because they are extremely adaptable to different environments, but also because solar panels are straightforward to manufacture, ship, and sell. But solar has a fundamental physical constraint, and that is its capacity factor. In most parts of North America, a solar panel produces its rated output for roughly 4 to 5 hours per day. Across a full year, that translates to a capacity factor of between 15 and 25%, meaning the average solar installation is doing essentially nothing for 3/4 of the time it is installed. Pico Hydro, by contrast, has a capacity factor of 95% or higher. If you have a 1 kilowatt hydro turbine, it produces 1 kilowatt every hour of every day. In 24 hours, you have 24 kilowatt hours. To get that same output from solar, you would need at least a 6 kilowatt array to account for the darkness and the angle of the sun. And this leads to a massive difference in battery requirements. Due to its lower capacity factor, solar users need a massive reserve of lead-acid or lithium batteries to bridge the gap between sunset and sunrise. Whereas a hydro user needs no batteries at all, or perhaps just a small buffer bank. Providing a suitable site with an all-year flow has been chosen, the stream is the battery. And the potential energy of water held at elevation is more consistent and more reliable than any chemical storage ever manufactured. This reliability and low technological barrier are exactly why Pico systems have been a lifeline for people living in some of the remotest regions on the planet. In remote villages in Nepal, Indonesia, and Kenya, where the grid is 1,000 miles away, community-managed microgrids of 10 to 50 kilowatts have transformed entire communities. They don't use high-tech, proprietary battery systems from Silicon Valley. They use Pelton wheels and ELCs. They have bypassed the 20th century grid entirely and moved straight into 21st century independence. But even in urban environments, this technology is proving its worth. Researchers in Australia have begun using energy recovery Pico turbines inside the filtration systems of commercial buildings. By capturing the pressure that is usually wasted in plumbing valves, they can recover 10% of a building's energy use. The principle isn't just for mountain streams, it's a universal law of pressure. So why, if this technology is so superior in respect to capacity factor, isn't there a turbine in every creek in the Appalachians or the Cascades? Well, the answer begins not with a corporation, but with an act of Congress. In 1936, the Rural Electrification Act created a federally subsidized program to extend centralized, high-voltage grid infrastructure to rural America. Before that act, if you lived in the country, you were responsible for your own power. You bought a Delco plant or built a water wheel. But by subsidizing the cost of running miles of copper wire, the government effectively removed the economic incentive for individuals to maintain their own systems. Over 2 generations, the skills required to maintain a Pelton wheel, the plumbing, the bearing maintenance, and the nozzle adjustment were lost to a culture of centralized dependency. We traded a free, local flow for the convenience of a monthly bill and centralized generation controlled by big industry. And today, the bureaucratic system can make it difficult to implement these systems. In the United States, the Federal Energy Regulatory Commission, or FERC, claims jurisdiction over any hydropower project that affects a navigable waterway. While there are now exemptions for very small projects, a run-of-river project on a natural stream can still require a permitting process that can take a year and cost thousands of dollars in environmental studies. Then there is the legal divide written into American water law. In the eastern states, the riparian doctrine applies, stating that if you own the land, you have a right to reasonable use of the water that crosses it. For a Pico Hydro system that returns 100% of its diverted water to the stream, this is generally workable. But in the western states, where most suitable hydro terrain is found, prior appropriation governs instead. Under prior appropriation, water is a separate property right. Even diverting a stream through a pipe for 30 seconds and returning every drop can be classified as a violation of a senior water right held by someone else. And of course, beneath both the federal jurisdiction and the state water doctrines sits the same structural barrier that has quietly excluded dozens of effective technologies from mainstream adoption: the absence of a supply chain that profits from continued use. While the upfront purchase of the turbine and materials can represent a notable expense, a well-built Pelton wheel can last for 50 years with nothing more than a new set of $50 bearings every decade. There is no recurring revenue for maintenance fees or part replacements. For those prepared to navigate the bureaucracy, Pico Hydro remains the holy grail of energy self-sufficiency. Yet, politics aside, there are still some things you'll need to take into consideration. The first barrier is the site itself. You cannot will a hydro site into existence, and for many of us, our environment simply might not lend itself to a Pico Hydro setup. You must have head and flow. You can measure head with a simple pressure gauge on a garden hose or a laser level. And you can measure flow with the bucket method, a simple test, timing how long it takes to fill a 5-gallon pail. If you don't have at least 50 feet of drop or 10 gallons per minute of flow, the economics fail before the design begins. The second barrier is maintenance. A hydro system is a living installation. Intakes clog after storms, bearings wear, and, in hard winters, pipes can freeze. This is not a set-and-forget system, and will require regular attention to ensure it remains at its most efficient. But for those who have the land, the water, and the willingness to maintain it, the barrier to entry has fallen significantly in the last 20 years. Out-of-the-box solutions offer the easiest method of adoption. Companies like PowerSpout and Scott Hydro now offer complete all-in-one turbine units designed to bolt to a concrete pad and wire directly into a modern inverter system. But for those working with a tighter budget, other DIY options are available. The first option begins with a piece of lateral thinking: the pump-as-turbine strategy. A standard centrifugal water pump, designed to move water using electricity, will actually generate electricity if you force water through it in the opposite direction. Because these agricultural pumps are mass-produced and sold at every hardware store, they provide a robust, industrial-grade core for a fraction of the cost of a specialized turbine. But the most accessible entry point for the independent builder currently comes from the open-source work of Daniel Connell. He has pioneered a high-performance open-source design that allows anyone to construct a functional turbine for less than $50 using common materials. I'll leave a link to his open-source website in the description below. His work is part of a broader global movement dedicated to open-source low technology, providing the blueprints for energy independence to anyone with a drill and a basic set of hand tools. By following these community-validated designs, you can bypass the specialized market entirely and build a system that turns a backyard stream into a continuous power supply. And remember, whatever path you choose, the single most important step happens before you touch a tool or contact any supplier. And that's to measure your dry season flow. Not the spring flood, and not the autumn average. Design for the flow the stream carries in August, at its lowest, after weeks of drought. A system that produces 500 watts continuously through a dry summer is more useful than a system that generates 5,000 watts for just 2 months of the year. The Pico Hydro generator is a bridge between the mechanical genius of the 19th century and the power electronics of the 21st, proving that a simple stream can provide more energy security than a decade of battery innovation. If you enjoyed this video, then I'd be grateful if you'd consider subscribing to the channel. We cover a lot of different tips and tricks that will help you live an off-grid, independent life. And if you want to see how a French farmer fulfilled all of his energy needs from a rotting pile of sticks, then take a look at our video on the biomiler here.